So, not sure what your feelings are right now on rate laws and mechanisms and table inspection, but if you're all right at those things, then you're going to make at least a 66 on my exam, yeah? Because it's two-thirds of the stuff. We've got one-third left. So, we are going to finish kinetics today with a look at temperature and catalysts, other things that affect speed. But before we do that, I thought it'd be fun to just revisit our temperature gauges. Since we're talking about temperature today, Fahrenheit, of course, the one that you're most used to. Um, we've all experienced 100 degrees Fahrenheit since we live where we live. You may not have experienced 0 degrees Fahrenheit. You probably had to travel somewhere to experience that, but it's survivable. Have you experienced 0 degrees Celsius?
Yes.
Yeah, because that's 32 degrees Fahrenheit, right? It's just freezing. So, I mean, we don't get it a lot of that, but we get it a couple times a year usually. What is the equivalent of 100 degrees Celsius to Fahrenheit? No. It is boiling. It's 212, 212.5. So we're lucky that we don't deal with over 200 degrees Fahrenheit outside. Now, Kelvin, our scientific scale that you got exposed to last year a little bit, what's true about 0 Kelvin and 100 Kelvin? They're both really cold. They're both super cold. That's absolute zero. But yeah, they're both so cold that it kills you. Anyway, you don't need to know that stuff, but we are talking about temperature today, so I made a couple alterations to the slide from you copying them, you watching this video. If you go to these slides now, it'll be exactly what it is here. But anyway, you still got all the info you need. I clarified a couple things, including the temperature. So here's what we're talking about. We're always looking at ways to speed up a reaction. If right now I were to give you chemicals and say, hey, go mix them in the lab, and it did something, and then I told you do it again but faster, your gut would probably tell you to heat it up. And for the most part, that's a good reaction because heating up the reaction generally makes it go faster. But I need you to know why, which is what this is. So focus in on what heating up a reaction actually does. Now, a couple things. First off, these two humps are supposed to be identical to each other. When I copied this over, I lost the top of that hump for some strange reason, so I tried to redraw it, and I know it looks like I had a seizure while I was doing it, but it's supposed to be another smooth hump. So it's funny, when I go and I look at the notes that y'all copy, like some of y'all like tried to copy my disease into your notes, and that's my bad. Anyway, the difference between these two, though, is the temperature, right? Here's why these reactants will react faster. First off, activation energy might be new to you. Activation energy is the amount of energy it takes for a reaction to start. That activation energy here in my diagrams is being represented by a dashed line going upwards. True or false? The activation energies in those two graphs are at the same point. It's true. So we need to make sure that we are good at reading graphs. That's a big part of science. But yeah, do you see how the dashed line's right below the 120 mark on both of them? All right. So it is in the exact same spot. However, this reaction has a lot more reactants reacting. Here's why. Look here. The activation energy is a value, a quantity of energy the reactants have to react. When it's hotter, there's more energy in the environment, and the reactants are able to absorb more energy. Therefore, more of them can hit that activation energy because they possess more energy. because there's more energy. That's what the temperature does. In the other one, where it's cooler, the reactants have less energy. Therefore, whatever that mark is, the activation energy that they have to get to react, it's harder to do it because there's less energy available because it's cooler, less hot. It's the better way to say it. Notice how changing the temperature does not change the activation energy. We've already said it, but it's important. However, there is a way to change the activation energy. Again, I just clarified the words that you wrote. Anyway, I've got two reactions again. But hey, what's true about the temperature this time? They're the same. I didn't change the temperature. However, for some strange reason, there's still a big difference. This bottom reaction has had a catalyst added. Make a note of that if it's not clear from what you wrote. This bottom reaction contains a catalyst. True or false? The activation energy is at the same spot for both of those graphs. False. Here, it's above the 120. Here, it's below the 120 because catalysts do change the activation energy. They don't change the temperature, right? We added a catalyst down here and the temperature stayed the exact same. But by adding a catalyst, the amount of energy required for the reactants to do their thing was lowered. The reactants still have the same amount of energy. It's just all of a sudden, it took less to react. And some of them suddenly had enough. They're like, I have the same amount I had, temperature's the same. But now it takes less energy to react, which was good for them. The last 6 minutes of me teaching is really important. And from my experience, only about half of you are with me right now. So what I'm going to do is teach it again. We're going to start over. But with a different example. So let's rewind, and I'm going to explain all of that one more time because I really want you to get it. Now, don't copy that. Busy board, right? The reason that you definitely don't need to copy this is because it's on Canvas. Some of y'all might have noticed that in between your assignments and my videos, there's a file there that you can click on. It's a picture of this. So if you end up really liking this, awesome. You can print it or copy it later, whatever. But right now, just listen to me. Let's start over here on this side of the green line. Look at my two different beakers. They're at different temperatures. Do you see how the top beaker's at 100 and the bottom's at 175? Different temperatures. The bottom beaker is hotter. These floating rectangles are reactants, and in them, I put the amount of energy they have, probably measured in kilojoules. We're not worried about that yet. But I wrote the amount of energy. So I want you to look at the 100-degree energies and compare them to the hotter energies. What's true? Yeah, the bottom beaker that is hotter, more energy available in the environment, the reactants have more energy. They're absorbing that energy. The activation energy for whatever this reaction is 355. I made up that number, whatever. 355. So look at the top, the cooler reaction. How many of those reactants can react? One. Just one. Because you have to have at least 355 to react. Only that one can react. But when I heat it up, how many of the reactants can react? Three. Because now that there's more energy available, the majority of them, except for that dude there, were able to reach the activation energy. So heating it up increased the kinetics. Let's go to the other side of the line. First, I need you to notice that this speaker and this speaker are identical in every way. Same temperature, therefore same starting energies of the reactants. Do you see it? And the same activation energy. So if I were to say, how many of them can react? You would say one, just that one, because of that activation energy. But here's what I do to the other beaker. I added a catalyst. Did adding the catalyst change the temperature? No, they are both still at 100 degrees Celsius. And look, the energies are still exactly the same. Look at the rectangles, the reactants. Do you see how none of that changed? But what does a catalyst do? It lowers the activation energy. The activation energy of this speaker is 325. With the catalyst, how many of those can react? 3. Because now that 325 is the mark, 3 of them are able to react. Temperature stayed the same. Amount of energy in the reactant stayed the same. But when I lowered the bar, more of them were suddenly eligible. And we got better kinetics. Questions? By definition, that's what it does. By adding a catalyst to an environment, the activation energy lowers. That's its purpose. All right. Let's move on. There are 2 categories of catalysts that College Board wants you to be aware of: heterogeneous and homogeneous. This is easy since you know what homogeneous and heterogeneous refer to, but in this case for catalysts, it's the phases. We're going to do heterogeneous first. A heterogeneous catalyst is one where the reaction and the catalyst are in 2 different states of matter. For example, let's pretend that we've got this gas and this gas that can potentially react together. The problem is, since they're gases, they move wildly and they have trouble colliding at the right orientation. I'm going to use that phrase a lot in a little bit. But they're having trouble reacting. We add a catalyst. Now, if it's a heterogeneous catalyst, it won't be gaseous. Maybe it's solid. 2 different states of matter, different hetero. And you know what can happen here? These gases can momentarily adhere to the solid, and there they are loving each other. By adhering to the solid, it lessened the chaos of their random motions, and we were able to connect, orient, collide, react them. A good example of this takes place inside of your car. Does anybody know what that's a picture of over there on the screen? It's called a catalytic converter. I want you to think about that phrase. Catalytic converter. Sounds like catalyst, and it sounds like there's a conversion of one thing turning into another. Inside your car, what happens is your car normally naturally produces carbon monoxide. And it does exactly this in the catalytic converter. And it converts that carbon monoxide to carbon dioxide and water for function of a bunch of things in the car. But the point is that it's this catalytic converter, a solid piece, that is allowing these gaseous items to react. It's usually made of platinum, and therefore that's a precious metal. And since it's made of platinum, catalytic converters are often sought after. You might have heard that people sometimes get their catalytic converters stolen while they're sleeping, and it's because they want that metal. That's heterogeneous. A homogeneous catalyst is where they're in the same phase. Yes. The red is the catalyst, the black is the substrate reactant. A homogeneous catalyst is one that's in the same phase. One of the most common places that you find this is inside of you, right? There's a bunch of reactions happening inside of you right now. And they're all in the same phase inside of your body for the most part. You do have a bunch of gases in your body, but enzymes are a biological catalyst that you have all throughout you that helps catalyze these reactions that you're undergoing. And they're in the same phase. But what I do want to point out about homogeneous catalysts is that they're super specific. It all has to do with shape most of the time. If you look at that image there, it's probably one that you saw in biology. But in order for this to work, the reactant has to perfectly fit inside the enzyme because these homogeneous catalysts, again, are super specific. And it has to do with the way they fit together a lot of times. We refer to it as a lock and key model. You know, your key only works for one lock. Another good example is a hand in a glove, right? That glove is built perfectly for a hand. It doesn't wrap around many other things well. Homogeneous catalysts are very, very specific on what they catalyze. But what's good about catalysts is that they're not used up during the reaction. They lower activation energy, but they're not used up to the point where they can usually detach and go and catalyze another reaction. We proved in our mechanisms that they weren't used up, because remember, they were still present at the very end of the mechanism. They regenerated, we say. Anyway, know that vocab. We can apply some of our temperature and energy measurements to an energy profile. So we messed with energy profiles a little bit with mechanisms, but I want you to know that there are some different measurable areas of a reaction in regards to energy changes. For example, in an energy profile, the very first hump does represent the activation energy. It's the amount of energy that it takes to start the reaction right there at the very beginning. So, good knowledge there. I do want to mention that at the top of the activation energy, we have what's called the activated complex. I don't see College Board ask about this like ever, but it's important to note that one step of the mechanism, basically, that lives at the top of the first hump has a special name. We call it the activated complex because it's that first baby step in the mechanism that's required for everything else to happen, which is just redefining activation energy, basically. But little vocab word hiding at the top of that first hump. You can quantify the amount of activation energy if you had numbers on these axes between where the reactants start and where that hump goes, and that would tell you, again, the value of the activation energy. I made up 255 or 355, whatever number I was using. But you can also measure energy changes between reactants and products, right? There's another arrow here where if you know the energy your reactant started with and the energy your products ended with, there's another measurable change there that you can also measure in or out. This mentions the word exothermic, which is not a big deal for us yet. It's coming. But if the products have less energy than the reactants, like they clearly do here, it's exothermic because energy was lost from start to finish. If this had started here and then it had done its little hump and ended up here, then the products would have more energy than the reactants. That would be endothermic. Again, I'm not testing you on that yet, but it's nice to mention when we're talking about this measurable difference between reactants and products. What is it? Is it something yummy? When y'all copy down that equation where you're like, dang it, that looks like it sucks. I got good news for you. In 2019, that's called the Arrhenius equation. They removed it from the curriculum. I know. Now, I can't find it in my heart to remove it from my slides because I don't think they should have removed it from the curriculum. But yeah, if you were taking this course 6 years ago or earlier, the slide after this one would have been calculation practice. But we don't do that anymore. Hooray for you. I am going to tell you what it is, though. But first, I want to talk about collision theory because this is really important. Focus. I'm tired too. When you're doing your FRQs and they're asking you all these questions on how to speed up the kinetics, and you're like, heat and catalyst, and you're showing off your brain and being all smart, inevitably, there's a point where they're going to ask you to justify it. Why? Why does all of this make it go faster? And here's where there are some key words that you need to mention. For reactions to happen, there are two big things that must take place. The reactants have to collide. Now, that's usually one that you can think of on your own, right? For a reaction to happen, the reactants need to come in contact with each other. But not only must they collide, but they need to collide at the right orientation. Collision theory says that oftentimes the reactants will collide at the wrong orientation and not react. Again, and not react. But there is a proper orientation where they do react. Which is why your justification for kinetics here needs to mention that while adding temperature makes things move faster and adding a catalyst lowers the activation energy so more things have the energy to react, that all of it can only happen if they're colliding a lot and at the right orientation. And that's why colliding a lot is a big deal. Because if you're colliding a whole bunch of times, the probability that you collide at the right orientation goes way up, right? So the two ideas are kind of married to each other. You need lots of collisions so that you have an increased chance at proper orientation, making the reaction go forward and fast. The Arrhenius equation that we're not going to be tested over is the equation used for finding activation energy. You would be given data and you'd be able to actually find this number for real, but now they'll just give it to you. To end the unit, we are going to discuss what's called the Maxwell-Boltzmann diagram. But in order for us to do that, we need to talk about nitrogen. Draw this with me, please. I'm going to trap 2 samples of nitrogen gas. My first sample is going to be sample A at 200 degrees Kelvin. The second sample, we're going to call sample B at 300 degrees Kelvin. Which sample? I haven't started. We're gonna draw kind of a particulate type thing, but which sample would you expect to have faster moving nitrogens? A or B? You're right. The hotter one. More energy, faster speeds, more velocities, more collisions. Let's draw some nitrogens. Draw them like this with me. So there's some nitrogens in container A. Let's draw some in container B. The length of the line is indicating the speed of the nitrogen. The length of the line that I drew with that arrow is indicating to us the speed of the nitrogen. Do you agree? Oh, I meant to go black. Do you agree that container B contains more longer lines than container A? So I did that on purpose, right? Because container A is supposed to be moving slower than container B. Are you with me so far? Those speeds that we speak of are average speeds. On average, container B has faster moving particles than container A. That is true. However, true or false, all of the nitrogen in container B is moving faster than the nitrogen in container A. It's false. Now look, I can prove it to you. That wasn't a trick question. See this faster one? There's a nitrogen. See this slower one? There's a nitrogen. Do you see how not all of the nitrogens are moving faster over there? That one's moving a lot slower than that one. On average, they're all moving faster. But if you go nitrogen for nitrogen, I can find faster ones in A compared to B. That's really important. They will trick you on an MCQ for sure if you don't understand what I'm trying to show you here. So overall, this one's faster than this one. Nitrogen for nitrogen? Not always. Because it's based on an average. Yes. The longer. When you're drawing a particulate in this way, yes. Now, that's not the Maxwell-Boltzmann, though. This is the idea behind it. Maxwell-Boltzmann is a graph. Draw this with me as well. And on this graph, we are going to plot number of molecules versus speed. If you were asked to graph this nitrogen data onto this Maxwell-Boltzmann, it's easy to do. Like in 2 minutes, you're going to think this is really easy. But on the surface, it confuses you at first. Watch this. Here's A. Here, let's hash mark this. So the speed is increasing. All right, and the number of molecules is increasing. But here we go. Here might be A. And here might be B. That's just like why does that make sense? Well, what's true about the number of molecules in A and B? The total number of nitrogens. Are they the same or different? Do you see how I put 6 in each? I did that on purpose. So the number of molecules in A and B are the exact same based on how I drew it. We know their speeds are different. Average speeds. So the 6 of A, the number of molecules are all represented right here with an average speed of 2. Whereas B, the faster one, has this more elongated curve because a lot of his molecules are going faster. Again, it's very logical, but y'all tend to think different. Like, y'all see this big hump, and you're like, ooh, man, he's going fast. Look how big that hump is. No, it means the opposite, because the majority of them are going slow. Let's try a non-Cummings drawn example. So take a look at this Maxwell Boltzmann, and let's draw our first card of the day. Let's go talk to cluster 2, seat 5. Hey, 2-5. Oh, I never checked y'all's notes, did I? No. Should we have the 2-5 be for the note draw? Yeah. Oh, is it? Oh, it calls on you a lot for notes? That's really weird. Y'all totally wait, you want me to call on someone else even though she has it? Alright, hey, at least y'all are protected from damage now. Anyway, let's draw another card. Let's go over to cluster 3. The 6. Hey, 3-6. Here's my question, 3-6. Of these 4 compounds, FeS6, F2, He4, or He3, which one do you think is moving the slowest? The guess is He3. Agree or disagree? Oh, they're being mean. Which one's moving the slowest? SEF, right? And again, I get because a lot of people thought the same thing that you said, because it misguides your brain. But yeah, in this case, the SEF6 is moving the slowest, because look, so many are just going this fast. Y'all want to draw another card? Yay! All right, let's go over to cluster 6, seat 3. Oh, Aspen. I didn't put Aspen out. My bad. I'm bad. It's 1-6. Let's just draw another card. Let's go to cluster 3, seat 4. Hey, 3-4. Yay, you're still here. Hey, 3-4. Of these 4 substances, which one do you think is being held at the highest temperature? Y'all agree with SEF? No, what is it probably? He3, because the higher temperatures move faster. It'll take a little bit of practice,